Yes, sir.
Okay, thank you. Okay. So basically over the next 1 or 1.5 hours, what I would be doing is that I would be giving you a brief idea regarding what is heuristic optimization. And more importantly, like it is a tool. And for electrical and electronics engineers, how this particular tool can be helpful. So there are, all of you might be knowing that optimization is a tool, or you can say that it is a branch of engineering, which has basically evolved to a very in a big way over the last 15 and 20 years. And you'd like most of you, whether you are working in VLSI design, whether you are working in signal processing, whether you are working in power electronics, whether you are working in power system, if you are doing active research, at some point of time you would have come across some work where optimization had been used for your particular domain. It may be how to optimize a particular circuit, the power requirement of a VLSI circuit. It may be how to design a filter. It may be how to design a power converter, or it may be how to design a power system stabilizer. So optimization is one domain which has found application in almost all the branches of engineering, and more importantly in the field of electronic and electrical engineering also. So in this particular lecture, I will be giving you a brief idea about what is optimization. And within optimization, basically now we have two groups of optimization technique. One is classical optimization, the other is heuristic optimization. So that is the first component of the lecture. And the second component of the lecture, which I think is more relevant, is that we will be talking about some applications of optimization in electrical engineering, and mainly with regard to system modeling and controller design. Right. So, during the course of my presentation, you can interrupt me as many number of times as you want. And you please feel free to ask any question. It may be the most basic of one, and it may be related to what I am discussing here. It may be related to your domain, not exactly related to what I am discussing here, but somewhat corresponding to optimization. Like suppose you are working in a particular area where you want to use optimization. So that also, if you have any question in that regard, you please ask me. I will try to answer that also. But you please ask questions that will give me a motivation, because then otherwise I will think that things are going over your head. Okay. So this is a brief presentation outline. And mind you, I would like to make this presentation as basic as possible. I would not be discussing about big research problems here that we have solved, but some of the my own experience regarding use of optimization over the last 15-20 years. And as an electrical or electronics engineer, how we basically have to, when we want to apply optimization, where we can apply optimization, where we cannot apply optimization. And if at all we are confident, we are convinced that optimization can be applied because some previous researchers have applied it, then what are the things that we have to do? Okay, so this is a brief presentation outline. First, I would be discussing about why actually do we need to go for optimization, and then formulation of the design problem into an optimization problem, how it can be done. So first you have to convert your problem into an optimization problem. And once you have formulated it into an optimization problem, what are the techniques that are available to solve that optimization problem? Now, as I have told, that those techniques can be broadly divided into two groups. One is what you call it as local optimization. The other is what you call it as global optimization. And then within a domain of global optimization, there are heuristic optimization techniques. Then I'll be discussing about heuristic optimization, and then I'll be going down to some applications in system modeling and controller design. Okay, so first I will be discussing about how to design the most simplest of controller, that is a PID controller using optimization. And then I will be discussing about system modeling, that I have a system, I don't know the transfer function of the system, how we can derive the transfer function of the system or the mathematical model of the system in terms of the state space equation or in terms of the differential equation. There, how we can apply optimization, that I would be discussing under differential evolution based parameter estimation. Differential evolution is a type of heuristic optimization technique. And then finally, I will be discussing about the design of optimal controller along with state estimation using optimization techniques. So mind you, my focus will be more towards the application of optimization for solving electrical engineering problems than on the actual optimization techniques, right? Now, just a minute. Yeah. So basically, in the title, I have mentioned two words. One is system modeling. The other is controller design.
Professor Ghosh, can you put it in a presentation mode?
Yeah, you're not able to see right now? Okay, okay. Sorry. Just a minute. I started using this. Yeah, just a minute.
We are able to see, sir, but it's not in the
No, no.
presentation mode, sir.
Okay, so just, so what I need to do? Yes.
Sir, there is a, you can see at the bottom, we have the window is there, na, sir. Select that one, sir. Third one, fourth one, yeah.
Yeah. Okay.
Yeah.
Fine. Actually, I moved to another slide. Now I think it is okay.
Yes, sir. Yes,
Okay.
sir. Yes, sir.
So
But
basically, I had used two words.
Slide is
there.
empty, sir.
No, I'm writing something here. Okay.
Okay.
So one is system modeling. The other is controller design. So basically, all of you know that we generally design controller, not generally, we always design controller for a system or a plant. And the most basic requirement regarding designing a controller is that the system model should be known to us. Okay, the model of the system. So when I talk of the model of the system, either it can be in the time domain or it can be in the frequency domain. Okay. So when we represent a system in the time domain, we generally represent by some ordinary differential equation, or we represent it in the state space form. And in the frequency domain, when we represent a system, all of you know that we do it by using transfer function. Now, the problem with designing a controller for real-time systems is that in most of the universities, we are teaching control theory in 5th semester. That is the first basic course on control system. Now, the problem is that whatever the theory that we are taught for control system, we are most of the times, 99% of the time, we assume that the system is a linear system. It is a time invariant system. But in practical world, 99.9% of the systems that we actually have to work on, they are non-linear system, they are time varying, and not only that, the non-linearity is of a very higher extent. Right? So, like the people who are working on power electronics, if you have to design a controller for a converter, now converter is a non-linear system because there is a switch that is involved there, which is making it non-linear. Now the problem is how to design a controller for a non-linear system. Okay. Now, so what basically we have to do, that non-linear system, first of all, we have to represent it by a model. So most of the times what we do is that particular non-linear system, we approximate it to a linear system and then we design a controller. Now the problem is, suppose you
Network is poor.
Yes, sir, it's not audible.
So network is poor, I think.
Yeah. Madam, I'm calling him.
Hello.
Sir.
But right now I'm not getting the rights, I suppose, to share it.
Yes, sir. Yes, sir. Yeah. Yeah. Sir, now we can get, sir.
It's still not showing.
Right, sir. Please stop sharing from your side.
Yeah, yeah. Now we can share, sir.
I can only see three options here.
No, please,
Chat, raise hand and push.
Oh, 1 minute, 1 minute.
No, please give host option to both, sir.
Yeah.
Yeah, join as panelist. I go.
Yes, sir. Yes.
Yeah, now it is visible, sir.
Now it's visible, sir.
Yes, sir. It's visible.
Now you can hear me also?
Yes, sir.
Yeah, sir. You're clear,
Okay,
audible,
right.
sir.
Okay, fine. So what I was talking that basically whenever we have to design a controller, we need to have the model of the system. When I say that we have to have the model of the system, it can either be the differential equation that represents the model, or it can be the state space equation that represents the system, or it can be the transfer function that represents the system. But most of the times what happens is that the system parameters are not known to us. The system parameters are not known to us. I have taken a very simple example. I have a system. It is let us for the time being, we assume that it is a linear time invariant system. And when I say that it is a system, more precisely, it is a circuit having some passive components. Let us say that it is a simple RLC circuit. Okay. But the value of the resistor, the inductor, and the capacitor are not known to us. There may be other elements also. Say something like this. We have more inductors, more resistors like this. Okay. A large number of passive components are there in the circuit. But when the circuit is given to you, the value of the passive components are not known to you. What you have available, you have only two wires at the input and you have two wires at the output. Okay. So it is like a black box. A box where only input terminals are there, two output terminals are there, and in between the input and the output terminals there are a large number of passive components, and the value of those passive components the value of the resistor, the inductor, and the capacitor are not known to us. Okay. Now your job to find out the transfer function of the system. Okay. So naturally, if you want to find out the transfer function of the system, you should know the value of the parameters of the circuit, which presently is not known to us. This happens for most of the systems for which we want to design a controller. So the problem is how to find out the transfer function, or how to find out the state space model, or to find both the transfer function or the state space model. The first thing that we need to do is that we need to find out the parameters of the circuit. Okay. So here, how optimization can be used, that we will see during the course of my lecture. The problem is clear to all of you. Now I ask you, do you have any solution to this problem? Which problem? Which is a very basic problem that we face most of the time in industry. That is, a circuit is given to us, but the parameters of the circuit are not given to us. We have to find out the parameters of the circuit. Why do we need to find out the parameters of the circuit? Because once we know the parameters of the circuit or the system, we would be able to find out the model of the system. And only when we have the model, we would be able to design a controller. The designing the controller comes as the next step. Okay. The circuit that I have drawn here, it may be a linear circuit, it may be a converter also. You may have a switch, you may have an inductor, you may have a capacitor. Okay. Somebody has given you that converter, and he or she is asking you that you design a PID controller for that converter. Now the question is how to arrive at the elements of the converter of the system or the circuit, right? So here how we can use optimization, that I would discuss during the course of my lecture. Now here the problem is optimization looks out to be a very promising solution, but most of the times the optimization techniques that we use, they are iterative techniques. When they are iterative techniques, their convergence is slow. It takes a lot of time to provide you the solution. Okay, most of the heuristic optimization techniques. So generally it is believed that we should go for optimization only when we don't have any analytical solution to solve the problem. Can anybody tell me the basic difference in between the two, what you know by an analytical solution and what you know by an numerical solution? Yes, anybody? Yes, please. Okay. Suppose
Somebody raised the hand, sir.
Yeah, please go ahead. You can unmute yourself and ask the question. What do you understand by an analytical solution to a problem? And the other is what do you understand by a numerical solution to a problem? Okay, let me tell you.
Sir?
Yes,
Sir?
please go ahead.
In case of analytical
Go ahead.
in case of analytical solution, we have set of mathematical equation and we can directly solve the equations. In case of numerical solution, we have to assume the initial solution and then we have to identify the final solution using the iterative mechanisms. And then
Yes, very good. Okay, fine. You are correct. Now, I have a very simple differential equation here, dy by dx plus py equal to q. Now, this is one differential. What you have said is absolutely correct. Now, let me elaborate it more. Now, suppose I have a differential equation dy by dx plus py equal to q, right? And you are asked to solve this differential equation. So, basically, what you will do is that when I talk of the solution of this differential equation, basically, you have to get an expression for y. So, this differential equation, it is a first order differential equation. You can apply the complementary function particular integral, or suppose if I, instead of dy by dx, suppose it is dy by dt, then you can apply Laplace transform also. Okay. But suppose your equation is something like this, because this is no longer a linear differential equation, this is a non-linear differential equation. Can you apply here complementary function or particular integral to solve this problem? Or for that matter, can you apply here Laplace transform to solve this problem? You won't be able to apply either complementary function particular integral or Laplace transform to solve this problem. Yes or no? You won't be able to do it. But then you have to get the expression for y. So here, the exact solution which you were able to get using complementary function particular integral or Laplace transform, it is not applicable. What you will do is that you will go for some numerical techniques. So you may be knowing about a large number of numerical techniques, say Runge-Kutta methods, Adams-Weishaupt method. So using those techniques, when you get the variation of y with respect to t, that solution we call it as a numerical solution. Okay, right. And you know that all the numerical techniques that we use either to solve a differential equation or for that matter an algebraic equation, they are iterative in nature. So what we do, we start from an initial solution and we go on updating the solution till a convergence criteria is met. Right. And you also may be knowing that most of the software packages, whether you talk of Mathematica, whether you talk of MATLAB, whether you talk of, for that matter, PSpice, all of them solve the equations corresponding to the circuit that you are simulating by using some numerical solver. Okay. So now you tell me, when you have two approaches to solve your problem, one is the analytical approach where you would be getting an exact solution, and the other approach is the numerical approach where you would be getting a solution which will not be 100% accurate, but it would be somewhat close to the actual solution. So when you would be going for analytical solution, when you would be going for numerical solution. For a problem, if the analytical solution is possible, why I am saying the analytical solution is possible? Because the equation that represents the dynamics of the system, that is not complex, that is not non-linear, and the analytical solution is available to you. So for such cases also, will you go for numerical solution, or you will go for numerical solution only when the analytical approach is not applicable there? Yes, please. I suppose you can type the answer in the chat box also.
So when the solution is achieved with the analytical way, then there is no use of numerical method.
Numerical solution. No, that actually, you're absolutely correct. When the analytical solution is available, in that case, you should not go for the numerical solution for the simple reason that numerical techniques are very much computationally intensive. Computationally intensive in the sense that when you write a code for that particular technique, since it is an iterative technique, it will take a large time to come down to the final solution. Whereas in analytical solution, you will get, it is a non-iterative approach. There is a clear formula by which you can apply to solve the problem. Now, optimization techniques, all the heuristic optimization techniques, they actually come under, all the heuristic optimization techniques, they come under this category. That is, it is a iterative technique. You have to start with a solution and then we have to go on updating the solution till we come down to a solution which is close to the actual solution. Right. Now, let us see here. Your job is to find out the value of R1, R2, L1, L2, and C. Okay. I again repeat the problem. You have a circuit. The parameters of the circuit are not known to you. Only thing that is available to you is that two wires which are the input, two wires which are the output. Okay. And some table is given to you. Something like when I apply a input of 5 volt, we get an output of 2 volt. When I apply a input of say 3 volt, I get an output of 1 volt. This table is given to you, or this table has been obtained by performing some experiment on that circuit. Now, what is your job? Your job is to find out the value of R1, R2, L1, L2, and C. Right. And from where you have to do it? From the input-output experimental data which is available to you. Now, when I talk of analytical solution would be something like this. If you have a formula where you have R1 as a function of V1 and V2, some direct formula is there, say some alpha V1 plus some beta V2 plus some gamma V1 V2. Right. Okay. So in that case, by taking only one experimental data, of course, the value of alpha, beta, and gamma are known to us. By taking only one experimental data of the input and the output, we would be able to get the value of R1. A similar formula exists for R2. A similar formula exists for L1, L2, and C. Okay. So what is the analytical solution here? This formula that you have derived, how you have derived? Based on your knowledge of circuit theory, you have arrived at this formula. Okay. Now that is the analytical solution. Once you have the analytical solution, you just put the data, you will get the value of the parameters. But things are not that simple. In 99% of the cases, this will not happen. That you cannot directly correlate one parameter with the input and the output of the system, because large number of parameters are there and there is a coupling in between those parameters. So in that case, how will you be able to get the value of R1, R2, L1, and L2 and C? Since the analytical solution is not known to us, in that case, you have to go for the optimization-based approach. So by applying an optimization-based approach, what you would be able to do is that you would be able to get the value of the parameters of the circuit, or you would be able to get the transfer function of the system from the input-output experimental data. This is what I would be explaining during the later part of my lecture. But first of all, you should convince yourself why system modeling is so important and why we go for optimization-based techniques instead of analytical solutions when we are trying to derive the model of a system. Model of a system basically means that either we are trying to derive the state space model or we are trying to derive the transfer function. So in the later part of my lecture, I would discuss about how we can derive the transfer function when the system parameters are not known to us, but the input-output experimental data is known to us. Right. So how that experimental data can be used to arrive at the parameters, and from the parameters, how to get the state space model. From the parameters, how we can get the poles of the system, zeros of the system, and finally arrive at the transfer function. This is what I am going to discuss in the later part of my lecture. So here, right now, what we have to do before applying optimization, you have convinced yourself why we are going for optimization, which is a computationally intensive approach, because analytical solution is not existing because of the, I am not saying non-linearity, because the system is still linear. Though it is linear, but because of the involvement of the large number of parameters, there is a huge coupling among the parameters. So it is a complex linear system. It is still a linear time invariant system, but it is complex. So for that, because of that complexity, analytical approach is not possible to derive the transfer function. That's why we are going for the computationally intensive optimization-based approach. So we are convinced that we have to use optimization for this. Now the next step is how to convert this problem into an optimization problem. Okay, right. Now that is actually very important. Most of the times what many of us do is that just for the sake of applying optimization, we apply optimization. I have seen some papers also in this regard, but there are simple approaches which might be available to solve that problem. If some simple approaches are available to solve that problem, it makes no sense to apply heuristic optimization, because unnecessarily you are using unnecessarily you are increasing the complexity of the problem. Now, instead of a complex circuit like this, suppose I have a simple RC circuit. Okay. Suppose I have a simple RC circuit, same problem, right? The value of R and C are not known to us, but the input-output data is available to us. Okay. Now, for this particular circuit, we know that what will be V2, the voltage across the capacitor. It will be, you have a switch which is closed at time t equal to 0. So what will be VC or V2? It will be V1 1 minus e to the power of minus t by RC. right? And suppose we are conducting an experiment, we apply an input. So this is the waveform that we will get in our oscilloscope as the output. And what is your job? Your job is to find out the value of R and C. Right. Now, here the value of R and C can be obtained without applying a numerical technique. Why? Because we know that at time t tending to infinity, okay, whatever the volt, like here, okay, at time t tending to infinity, this will be open. So V2 will be equal to V1, right? And here you can get RC, that is a time constant. But what will be the value of RC? You find out the time constant tau. What is that tau? It is the point at which the voltage across the capacitor reaches to 66.6% of the final value. Okay, so you can find out tau. So finding the value of tau, for that no optimization is required. Why? Because you can directly get it from the response of the system. And finally, what would be the transfer function of the series RC circuit? The transfer function of the system is 1 by 1 plus tau s. And what is this tau? Tau is the time constant which you can get it from the response that you are capturing at the output. This you can get it in the oscilloscope. So this tau can be obtained from here. Once this tau is obtained, you can get a transfer function, because the transfer function is 1 by 1 plus RCS. So for this particular circuit, finding out the transfer function does not require a numerical approach, or for that matter, an optimization based approach. It can be easily available. Why it can be easily available by an analytical approach? Because this equation you have. Okay, right. By using this equation directly, you can get the value of the time constant, and in the transfer function, you don't have to know the value of R and C separately. You only have to know the value of the time constant. So for this particular circuit, if you have to find out the system model, it does not make any sense to go for optimization. Whereas for this circuit, where the complexity is quite high because of the coupling that you have among the parameters of the circuit, which makes the system, the system more complex. That's why you have to go for a optimization based approach or a numerical based approach. Okay. So this was all about. See, I'm not going into optimization because again and again I tell students that if you are applying optimization, optimization is a very powerful tool. You can solve a large number of non-linear complex problems by using optimization. But first of all, you have to convince yourself when you should go for optimization and when you should not go for optimization. Like here, optimization can be applied for this problem, but for this problem, since a simpler approach is available, an analytical approach is available, you should not be going for optimization to find out the parameters of the circuit or to find out the transfer function of the circuit. Okay. So in the next stage of my presentation, I will be discussing about once we are convinced that optimization can be applied, how that parameter estimation problem can be converted into an optimization problem, and then how that once it has been converted into an optimization problem, how we can go for heuristic optimization. Now the second part of the presentation is about controller design. By the way, anybody has any doubt, please ask me. Just one or two questions I would like to take, please, regarding whatever that I have discussed till now. Or you can actually you can type your question in the chat box, because I understand all of you cannot be unmuted at the same time. Yeah, at least you can type your question in the chat box, right? No,
Sir.
No, yes, please go ahead.
Machine learning, data science also they are using optimization.
Okay. Now see, when I am saying data science, so let us right now, I'm not going into machine learning, deep learning and all that. So data analytics basically here refers to, let us talk of the same problem from the aspect of data science. So you have a huge amount of data. So what is the data that is available to you? Huge amount of data in the sense that variation of V1 with respect to variation of V1 with respect to variation of V2. Huge data is available. Right. Now, let me try to make the problem even more complex. The value of R1 and R2 are not constant, but they are changing with time. So previously we had a linear time invariant system. Right now what we are having is a linear time varying system. Okay. Now if you look at the two problems, now most of the systems that we have, even the simple circuits, a simple RLC circuit is not a linear time invariant circuit, it is a linear time varying circuit. Okay. Because to whatever minor extent, the resistance changes with temperature and all that. Now, I have made the problem somewhat more complex in the sense that R1 and R2 are not fixed, but they are changing with time. So naturally, the transfer function of the system will not be fixed, it will be changing with time. Now, I ask you a question. The volume of data that we would have required to solve the problem when R1 and R2 are constant, relative to the problem where R1 and R2 are not constant, the volume of the data that would be required, would it be same for both the two cases, or it would be different for both the two cases?
Different.
Data I am talking of, the data of V1 and V2. So naturally, when your system is time varying, you should have huge amount of data to capture the time varying nature of the circuit. Okay. Now suppose though my circuit is time varying, that is R1 and R2 are changing, but the data that I have is only for a certain instant of time where R1 and R2 are constant. So will that help you to solve the problem? That will not help you to solve the problem. If your circuit is time varying in nature, you should have data which captures the dynamics of the system when R1 and R2 are changing, right? Suppose for the first 5 minutes, R1 and R2 are constant. For the next 5 minutes, R1 and R2 are changing. But you have captured the data for only the first 5 minutes. Using that, you arrive at the transfer function. Will that transfer function be applicable always? That transfer function will not be applicable always. Why? Because you have not captured the total dynamics of the system. By total dynamics, I mean the time varying dynamics of the system. Now, here comes the importance of data science. Okay. So data science in the sense that basically when we go for data analytics, we generally consider that huge amount of data is available, right? So if your system is having more time varying nature, more complex nature, or even more non-linearity, in that case, the volume of the data that you would be needing to design to arrive at the model of the system, that would be high. Then you can go for the data analytics approach, say artificial intelligence, machine learning, and deep learning. So let us look at the stages. If your problem is very simple, like a simple RC circuit, you can go for an analytical approach. If your circuit is complex, but it is still linear and time invariant, then you can go for optimization based approach. Okay. And in the third stage, your system is highly time varying as well as it is non-linear. Then you have to go for, there also you can go for optimization, but some advanced optimization techniques with the association of data science techniques like machine learning and deep learning. Okay, so you can, like whatever the two stages that I have discussed here, you can think of data analytics and machine learning as a step ahead to it. But there is, most of the times, there is a very thin partition between optimization techniques and some machine learning techniques. There is a lot of similarity in between the two. Because ultimately in machine learning techniques also we are minimizing something or maximizing something. Okay, right. Okay. So whenever you are having maximization or minimization of something, there actually that optimization comes into the picture. Right. Okay. Okay. I suppose the question is answered. Yes. Anybody, please. Okay. Now, let me see if I have got any questions or not. No, not this. Now, let us now go for the second approach, which is the controller design. Now here, I think this is one block diagram, which all of you have come across multiple number of times. Okay, now you have to design a controller. So what we did in the first case, we arrived at the transfer function here. Okay, because previously we were not doing the transfer function. We had to design a controller. We should know the transfer function. So now by applying this optimization or analytical approach or some machine learning based technique, we have arrived at the transfer function. Now we can go for the controller design. Okay, let us say that it is the most simplest of controller, a PID controller. So you have error going as an input to the controller. So it is Kp into E plus Ki into integral of E dt plus Kd dE by dt. Now why you have gone for PID controller? Because the actual system in open loop was not performing properly. Why it was not performing properly? In the sense that the sort of output which you desired for a particular input, that was not proper. Hence we went for this controller design, right? We have converted the open loop system into a closed loop system. Now the problem is how to get the value of Kp, how to get the value of Ki, and how to get the value of Kd. So this is your problem. But what is your objective? Your objective is that the response of the system should be proper. The response of the system should be proper. Most of the times the response is quantified in terms of this error. Lesser the error at transient and steady state, we say that better is the response of the system. But somehow right now this error is quite high because the value of Kp, Ki, and Kd that you got is, suppose the response is highly oscillatory. Okay, this is your y of t and this is your r of t. Okay, so in the sense that you wanted that the output should track this r of t, which is this yellow line, but right now your output is not tracking the yellow line, which is the value of rt. There is a steady state error in between the two. Now you suppose you want to run your motor at 1500 rpm. It is oscillating at around 1500 rpm and finally settling down at 1600 rpm. So the response of the system is not proper. Whatever the controller that you have designed for the motor, that is not proper. So now you have to think of the PID controller. Okay, you have to change the value of Kp, Ki, and Kd. By the way, can anybody of you tell me how you design a controller? A PID controller. Let us, for the time being, we forget about optimization and all that I have discussed. Now let us just answer it from the control point of view. How we, for any transfer function that is given to us, if we have to go for the closed loop control and we have to design a PID controller, how will you design that PID controller? Or more specifically, how you can get the value of Kp, Ki, and Kd? Yes, anybody?
Someone is right answer.
Please go ahead. Yeah, if you have a
Sir, shall we use the Jaglas-Nicholas method, Jagel method?
yeah, there are certain approaches to find out the value of Kp and Ki. Now you are absolutely right when you say that the most common approach is by using the Ziegler-Nicholas test. Is by using one technique which you call it as the Ziegler-Nicholas method. But most of the techniques that they have their own limitation, in the sense that like this particular Ziegler-Nicholas method, it cannot be applied if your system is this unstable. Okay, right. So here, most of the times we go for optimization based PID tuning of PID controller. So we are convinced here that we have to use optimization to find out the value of Kp, Ki, and Kd. Why? Because the techniques, just a minute. Because the analytical approaches, one of the analytical approaches is by using this ZN, that is a Ziegler-Nicholas. Those analytical approaches are not applicable. Right? Okay. Maybe your system is unstable, that's why you cannot apply ZN method, the Ziegler-Nicholas method, which is the most common approach for finding out the value of Kp, Ki, Kd. Now you have to apply optimization. When you have to apply optimization, first of all, somewhere you have to write what is your objective and what basically you want to come out with by using optimization. Okay, what is your aim? there is a very small difference in between objective and aim here. Dictionary meaning both are same, but here there is a small difference. My aim is what? My aim is to find KP, KI, and KD. Okay. This is what you want. This would be the solution to your problem. And what is your objective? Your objective is to reduce error. Which error? I'm talking of this error. That is the difference in between the reference value and the output value. This one. Are you able to follow this? Before applying the optimization problem, you have to write it somewhere. What do you want and what you want to get from optimization? What do you want? You want to reduce the error. How you would be reducing the error? By getting the best value of KP, KI, KD. Now here also for this system model problem, what was the objective? What was the objective? The objective was to find out the value of R1, R2, C1, C2 and L so that the output that we would have got by simulating that particular circuit would be same as the experimental output. Okay. And what was the aim? The aim was to find out R1, R2, L and C. And the objective was what? Objective was to get an output which matches with the experimental output. Okay. I may take 10 random values of R, L, C and all that. Among those 10 random combinations of the parameters, which one of them would be the most suitable? The most suitable would be the one which would provide me the same output as I would have got it experimentally. So here also there is some error. Are you able to get it? What is that error? That error would be the difference in between the experimental output and the simulated output with some random values of that. Now that particular combination of the parameters which provides me an output which is equal to the experimental output, that is the best value of the passive elements. So here also we are reducing error. Here also we are reducing error. Here we are reducing the error in between the actual output of the system and the reference value. Here also we are reducing the error in between the simulated output and the experimental output. The simulated output, how you can get? You can simulate this model in MATLAB, in PSpice, in Mathematica. But for that, you should know the value of R, L, and C. Okay. So here, once you arrive at a simulated output with some value of R1, R2, L1, L2, and C, which matches with the experimental output, it means what? Your simulated model is exactly equal to the actual system. Hence, you have correctly estimated the parameters. So here the error was in between the simulated output and the experimental output. When you are modeling the system and when you are designing the controller, the objective was to reduce the error, which is the error in between the reference output and the what you call the actual output. So how will you reduce the error in this case? By arriving at the proper value of R1, L2, and C. And in this case, how you would be arriving at the, how will you reduce the error? By taking the proper value of K1 and K2. Sorry, KP, Ki and Ke. Okay. So now, I've taken a lot of time, but yeah, this main thing is, my idea was not to discuss too much about optimization and all that. But first of all, see, if you want to apply optimization, large number of techniques are available and there are large number of software tools that are available. Now, what is more important for you is that you properly frame your problem into an optimization problem. After you have framed your problem into an optimization problem, things are not that difficult, because it is my experience that more or less most of the heuristic optimization techniques will give you almost similar result. But the main challenge is that, and once you have converted your problem into an optimization problem, it is pure mathematics and programming. No electrical engineering is involved here. Once you have converted your problem into an optimization problem, you have the code, you give that objective function. I will tell you what is objective function. You give that objective function to the code. That code, most of the times, that codes are readily available and you have to make some minor changes in it. You will get the result. Of course, if you have to improve the result, you have to start writing your code from scratch. But initially it will give you some idea. But if you are not able to solve your problem into a proper optimization problem, then irrespective of how good the optimization technique that you use, you won't be getting you at the proper solution. You won't be getting a solution. That solution will be optimal from the optimization point of view, but it won't be optimal from the system point of view. Okay, this is one thing that anybody who is thinking of applying optimization to your research problem, you should keep that in mind. Okay, just a minute. I will still carry on with this, and then I will. If anybody has any problem, please ask questions.
No, sir, you're perfect.
So now, the next step is formulation. And Madam and Naresh, I think, see, I'm not that comfortable with the slides and all that. Like if I go to the slides, I think, is it better that I carry on with the way that I am proceeding?
Yes, sir. Please, sir.
Yes, sir. No problem.
No problem, sir. We're able to
Yeah.
understand. It's good.
No, the
Please.
thing is that I understand that most of your students are BTech or MTech students. If I take any research problem and I start discussing it, they may not get a feel of, but first of all, they should understand the basics. Okay.
It's
So
a combination, sir. UG, PG, and
Yeah,
scholars are
okay.
there, so no problem at all.
Exactly. So I can share the slides, and then if you have any specific problem, then you can take that question offline. Formulation as an optimization problem. Formulation as an optimization problem. Okay. So formulation as an optimization problem basically means that how we can convert that system modeling problem into an optimization problem. Okay. Right. So previously what we did, first of all, we had written the objective, and then we had written the aim. And before that, we had convinced ourselves that for this particular problem, analytical approach cannot be used. So we are going for optimization. We have written the objective. We have written the aim. For the controller design, what was the objective? The objective was to reduce the error. And the aim was to find out the value of three parameters, KP, KI, and KP. Okay. Now the next question is how to find KP, KI, and KD by using optimization. Right. Okay. Now, this is one problem that most of you might have solved in your school, maybe in class 10th or 11th. A function is given to you. You are asked to find out the value of x for which f of x is minimum. This is the principal optimization problem. Okay. Either you are maximizing it or you are minimizing it. So this problem looks out to be very simple. It is actually very simple. So what is the most classical approach of solving this problem? What we did, we took f dash of x is equal to 0, and then we solved it. Suppose we got f dash of x is equal to 0 at x is equal to x star. Then in the next step, what we did, we took f double dash of x, and then we calculate the value of f double dash of x at x equal to x star. Now, if this comes out to be positive, we say that f of x is minimum at x star, and if it comes out to be negative, f of x is maximum. This is one thing I suppose all of you know about it. It is a very simple approach of maximizing or minimizing a function. Right. So now the question is, had optimization been so simple, why you would have so much of research papers written on optimization? Where you would have been so much of what you called like operation research has come up as an altogether new field, right? So then why would have so many problems still unsolved by using optimization? Now the problem is, why this approach? The problem remains the same. But why this approach cannot be always used? By the way, this particular approach is an analytical approach or it is a numerical approach? This is a pure analytical approach. Okay, because f dash of x is equal to 0 is solvable. Right. Suppose it is a cubic function. Once we take the first derivative, we get a quadratic equation, and then the quadratic equation we solve, we get extra. Now, this particular problem is a pure analytical problem. No numerical approach is required. Now, the problem comes when this particular function f of x is nonlinear. And let us say for the timing it is not nonlinear, I would say that it is highly nonlinear. Suppose f of x is something like x cube plus log x to the power of 5 by 2 divided by e to the power of x into x to the power of 1 by 2 into x cube. Okay, something like this. Okay, again some complexity. Right. And more complexity can happen if x is changing with time. Now, is it that simple to find out the derivative of this function? Is it that simple? Yeah, I have considered an exponential function. Yes. So, is it that simple to find out the derivative of this function? It is not that simple. Okay. So, again, if you have to find out the derivative, in that case, what you have to do? You have to go for a numerical approach. Now, the problem comes when this function f of x is nonlinear, it is time varying, it is complex. So, for such scenarios, you cannot directly apply this classical, this I am taking it as the classical optimization technique. Mind it, whenever I'm talking of optimization, I am maximizing something or minimizing something. Right now, I am minimizing the error for this particular closed loop system. Okay. So, if the function is so complex that the differentiation not exists, it is non-differentiable. And if there is a discontinuity, suppose the function f of x versus x is something like this. Can you find out the derivative of f of x at x is equal to x star? It is not possible because the function f of x has a discontinuity here. So what I mean to say is that for most of the real world problems, this function x is non-differentiable. So since it is non-differentiable, this approach of finding the minimum or maximum of a function generally is avoided, or it is not possible to say. Then you have to go for numerical approach, and the easiest or the most common numerical approach for optimization is by using heuristic techniques. Now here, for this problem, what would be f of x? What is this f? F is your objective and x is your aim. You are trying to attain the objective by finding the proper values of Kp, Ki, Kd. Suppose error is here. So what is your objective? Your objective is to reduce the error. So what would be f of x for your problem? F of x is called the objective function or the function that you are trying to minimize. So f of x for your case will be error. Or for that matter, f will be error, the function will be error because you are trying to minimize the function. Now, can you tell me what will be x? X will be, error is dependent on what? The transfer function is fixed. You want to change the output. So the only option available for you to change the output is to change the value of Kp, Ki and Kd. Okay. So your function is error and the x, that is the independent variable of the function, is Kp, Ki, Kd. Are you able to get it? So you are having error as a function of Kp, Ki, Kd. So what is your aim? Your aim is to minimize this error. How you will minimize this error? You will minimize this error by finding the proper value of Kp, Ki, Kd. Okay. So what is your objective? Your objective is to reduce the error, and that reduction in the error, for that you have a aim to find out the optimal value of Kp, Ki, Kd. So here The parameters or the tuning parameters of the optimization problem are Kp, Ki, Kd. Are you able to get it? So this is what you call it as the objective function. Now, the main challenge for an electrical engineer or an electronics engineer is to arrive at this particular mathematical equation. Once you have arrived at this mathematical equation, what is that? F of x. It is a not a single variable problem, it is a 3 variable problem because this x is again made up of Kp, Ki, Kd. Okay. Now finding this function is the main challenge. Once you have obtained this function, which most of the times we are calling it as an objective function, in that case, there are techniques to find out the minimum of it. That is the heuristic optimization technique. But if you have not, whatever the heuristic optimization techniques are there, whether you talk of genetic algorithm, differential evolution, particle sum optimization, I am not going through these techniques. Keep in mind, most of the times they would provide you a solution which is almost closer to it. People are doing it for the sake of publishing papers. But mind it, if your f of x is wrong, whatever the technique that you apply to find out the value of x for which f of x is minimum, that will be optimal from the optimization point of view, but that will not be optimal for the overall system point of view. Okay, so mind it, framing the optimization problem is one step. That is converting your problem into an optimization problem is the first step. The second step is using a technique to solve that optimization problem. And I will say that it is the first step which is more important as compared to the second step. Second step, I won't say that it is not important because if you have to apply a good technique. But if there is a problem with your f of x, whatever the technique that you apply to minimize it, the final solution that you would be getting won't be proper. Okay. So always keep in mind, formulation as an optimization problem is very important. Let us take the case of a very simple RC filter. Suppose I have a low pass filter. Okay, R and C. Right. Now using this filter,
Hello? Sir, is it
yes,
audible? Yeah.
yes. Yeah. Yeah, any question or just you wanted to check? Naresh?
No, sir, go ahead. Go ahead. Everything is clear to us.
Okay.
Just I want to check, sir. That's all. Yes, stop.
Now, filter design is also one area where optimization has been very, widely used in recent times, mainly with regard to designing finite impulse response filters. I mean, like suppose if you have a two-dimensional filter, which would be used for image processing, there also, this optimization has been very widely used. Now, let us take the case of a very simple low-pass filter. I have a RC circuit. Now, you have to find out, or you have to design the filter. Now, here you have an analog passive filter. So, what is your aim? Your aim is to find out the value of R and C. Okay, so that this particular filter has a particular, crossover frequency, say of 150 Hz. Okay, right. So, any idea how you can get the value of this R and C? Now, for this particular problem, you know that there is a formula exists, FC is equal to 1 by RC. So you can direct apply that formula. You don't have to go for optimization. Right. But suppose, let us take the case of a IIR filter or a FIR filter where the number of parameters are quite high. Right now, the number of parameters are R and C, only two parameters are there. So you may not have to use optimization here. Now, can you tell me when you are designing a filter, what is your objective and what is your aim? So what is your objective? Your objective is to meet the specifications of the filter, like what may be the ripple in the pass band, what may be the ripple in the stop band, what may be the cutoff frequency. These are your objectives. And how you would be meeting those objectives? By tuning the parameters of the filter. Okay. So in that case, what will be f of x? Physically, what will be f of x? F of x would, you have to come up with a mathematical equation that correlates the objective of the problem in terms of the cutoff frequency, in terms of the ripple in the what do you call pass band, stop band. Okay, right. Now, in this case, what is the error? How many errors that you have? Error in ripple, error in FC. Okay, right. So you have to reduce the error in the ripple. What I mean by the error in the ripple that you are getting from your filter and the ripple that is actually you are aiming out for. They say that the ripple should not be greater than 2%. Okay. So 2% minus the ripple that you are getting, that is the error. Okay. And what is the error in the cutoff frequency? The cutoff frequency that you are getting with the cutoff frequency that is asked by the client, which is 150 Hertz. So it is 150 minus the cutoff frequency that you are getting. Okay. So there are two errors here. These two errors, you have to make it 0. So how you can make it 0? By taking the proper value of R and C. Not R and C, there will be, since there are more circuit elements involved here, there will be more resistors and more capacitors. Okay. So what you would be doing, a very crude approach to solve the problem is to take some random values of the parameters, keep on changing it till this error becomes equal to 0 or this error becomes equal to 0. That is an ad hoc approach. If you look at the optimization based approach, in that case, what we do is that we quantify this error. We come up with a function which represents the error in terms of, say, R1, R2, C1, C2. Okay. And then we try to minimize it. Error becomes f, the function, and the parameters x becomes R1, R2, RC. And then we apply some technique to get the value of x for which f of x is minimum. Now you tell me which is more important, the technique that you apply to solve, to minimize this is more important, or to come up with the mathematical equation of f of x, or to find out a mathematical equation that correlates error with R1, R2, C1 and C2 is more important. If you are not able to frame this function properly, you may apply the best technique, but since your problem is incorrect, even if you are getting a 100% accurate solution to the problem, the solution is still inaccurate because your problem was improper. There was a factual error in your problem. So always I will tell you, whether you are using optimization for filter design, whether you are using it for image processing, whether you are using it for converter design, whether you are using it for finding the transfer function, or whether you are using it for, say, controller design, always make sure that the objective function f of x that you have formulated is correct. So step by step, if you see, first of all, you have to convince yourself that this problem is complex. There is non-linearity in this problem. We have to go for optimization because there are numerical techniques that are, analytical techniques that are not available. I have gone through the review of a large number of papers where they have applied the best optimization technique, the most recent optimization techniques. Suppose I am also one of the reviewers, and finally, when actually the papers gets rejected, you get to see what the other reviewers have also told. So what I see is that many a times I have seen myself and other reviewers commenting that this is a problem for which you should not have applied heuristic optimization. Why? Because since your problem requires a faster solution, if you want to solve a problem for which the solution has to be obtained in real time, you cannot go for an iterative technique. In real time, within a very small interval of time, you have to minimize f of x, which is not possible with heuristic optimization, but still people have used it. Okay. So many a times I see a comment like this, that this is a problem for which heuristic optimization should not have been used. Right. Still you have used it. You have made the problem more complex. So your paper gets rejected because there is a problem in the paper at the very basic level. You are You have applied optimization only because you are motivated to apply optimization, not because you have to solve a problem. Think over it. Look at the problem. Don't look at the optimization technique. If your problem is solvable by some other technique, you have to convince yourself why you are going for optimization. You cannot apply optimization. Whenever I am saying optimization here, I mean to say heuristic optimization, right? So whenever you are applying heuristic optimization, you don't apply heuristic optimization just for the simple reason that nobody has applied this particular technique for this particular problem. Okay. It should be a contribution, not from the application point of view. It should be a contribution in terms of finding a better solution to a solution which already exists. This is a problem which most of the researchers make. Right. So convincing yourself is very important. Once you have convinced yourself that, yeah, we should go for optimization, that will be an add-on to the present state of art of the solution to this problem. Then you go for optimization. And then the next thing that you have to do is that you have to know what are the things that are unknown which you want to find out from the optimization problem. Like in this case, KP, Ki, and KD are the unknowns. In this case, the value of R and C were the unknowns. So this will be your optimizing parameters. Okay. This will be your optimizing parameters. And then through those optimization parameters, what is your final objective? Your final objective, most of the times it will be error. Especially for controller design, it will be error. And for image processing or signal processing, sometimes it will be power. Sometimes, because suppose those of you who are working on VLSI circuits, like you might have seen that over the last few years, optimization techniques has been tremendously used to minimize the power dissipated by a particular circuit, because most of the circuits, they are very power hungry. Okay, so their optimization has been used to a very large extent. So think over whether you are reducing error, whether you are reducing cost, whether you reduce cost. People who are working in power system engineering, like you are solving that economic load dispatch problem, where you have to, a particular load, you have to divide it among different service providers. So what is the minimum tariff for a consumer that you are trying to reduce? So that is again an optimization problem. So whether you are reducing error, whether you are reducing the cost, okay, or you are you are maximizing the efficiency, okay. So that is your objective. And the final step is for formulation, you have to correlate the objective with the optimizing parameters, or for that matter, you have to come up with a mathematical function that mathematically represents the objective of the problem in terms of the parameters of the problem, which is f of x. Okay, that we call it as the objective function. And then once you are very sure that this objective function that you have framed, it actually represents your system, it actually contains in itself the objective and the aims of the problem, then you have to select the optimization technique. Okay, right. Okay, so yeah, anybody has any question, please? So Naresh, how much more can I continue?
Sir, you can continue.
Okay. So just a minute.
For another half an hour, sir.
Yes, madam.
For another half an hour.
Okay.
Yeah.
Sir,
It's your wish, it's so interesting.
One attendee raised the question. 1 minute, sir. Jagdish, welcome.
Yeah, I think if you can ask questions, that would be more proper. Because see, again and again, I'm telling you, if I go on discussing about genetic algorithm, if I go on discussing about differential evolution, or for that matter, particle sum optimization, these are the heuristic optimization techniques you people have gone through. Okay, so I don't think, first of all, there is not too much of mathematics which is involved there. Right. So
Yes,
again and again, I'm saying it is, as an engineer, it is a tool. Okay. Optimization is a tool, but the first thing is that you should be able to frame your
Recording in progress.
Right. Okay. I think I will answer this question. Okay, let me answer it just a minute. So your problem is you have to minimize this function f of x, and here x is a two-dimensional vector, okay, or x is made up of x1 and x2. Right. Now, just a minute. So now, see, every point within this rectangle, it represents a particular value of x1 and x2, right? And for that, every value of x1 and x2, I have a value of f x1, x2. Yes or no? Yes, Jagdish? Right. No. So I have infinite number of points within this x1 and within this rectangle, infinite values of x1 and x2, like everywhere. So many points are there, infinite points are there. And for each of those points, f of x1 and x2 are there. Now you have talked of two things. One is exploration. The other is exploitation. All of you know of something called treasure hunt. Okay. Yes. So in treasure hunt, what we do, that within a particular assigned area, we try to find out a particular treasure which is kept here. You think of that. So there is somewhere we start with a particular point, and then from here, one person starts from here, another person starts from here, another person starts from here, another person starts from here. Now, the value of, at this point, the value of f x1, x2, within this green region, the value of x1, x2 is less than 5. Within this region, the value of x1, x2 is less than 4. And within this region, the value of f x1, x2 is close to 0. You are trying to minimize this function f, which is a function of x1, x2. Now, which is the best point? Here, in this two-dimensional plane, which is the best point? The best point is the point where the value of this function is minimum. And the best point is somewhere here. That is the yellow circle that I have drawn here. Okay, here the value of the function is close to 0. All the points within this black region, the value of the objective function is close to 0. But right now you don't know, okay, that this is minimum point. If you don't know this is the minimum point, what you will do, suppose 5 of your friends, you start from different points. One starts from here, one starts from here, one starts from here, one starts from here, and one starts from here. And then randomly you go on moving in different directions, okay? To find out the treasure, or to find out the point in this x1, x2 where the value of the objective function is minimum. Right? So what happens? These 5 friends, they move in different directions. Each time what they do, whatever the value, suppose the first friend starts from here and after some time he reaches here. Now once that friend reaches here, he finds out the value of f, and that value of f is communicated among the different friends. So this is the exploration phase. Why I am calling it exploration?
because I have started with some random points and I am exploring the search space. What is your search space? The entire search space. Randomly, I am exploring in different directions. Okay. So that I am able to reach this point where the treasure is kept. So you are exploring. How you are exploring? By randomly moving in different directions. Okay. Now suppose after that random movement, one of the friends reaches here. The other friends are far away from this point. And this friend, he communicates with the other 4 friends that I have reached a point which is very close to the optimal point. So all of you should now not move randomly, but you should move towards me. Why you should move towards me? You should move towards me because I have reached a point which is close to the treasure. So then what all of them do is that they try to move towards this point, which is close to the optimal solution. So in the initial phases of the optimization problem, in the initial iterations, randomly you are changing the value of x1 and x2. You are exploring the search space. Now, after some point of time, when you are closer to the optimal solution, you are exploiting the present solution. You are exploiting it. What you are exploiting? You are exploiting the goodness of the present solution. And you are trying to make the other values of x1 and x2 move towards it. So that is exploitation. So after some point of time, what will happen is that all the points will converge toward this and then they will finally converge at the optimal. Okay. Now this exploration and exploitation phase is there in most of the heuristic optimization techniques, right? Like one common is, I think this many of you might have heard of, it is called ant colony optimization. Okay. So if you have seen the movement of ants on the floor of your house, what you will see is that generally, initially, these ants are moving randomly. Okay. But after some point of time, you will see that all the ants, they move in a particular line and they follow a particular direction. Say somewhere some sugar is kept or some sweet is kept. Okay. Then they follow that particular pattern. But before following that particular pattern, they are randomly moving in different directions. So here also, you are randomly changing the value of x1 and x2 in different directions because you want to explore the search space. And once you have explored the search space, some of you might have come closer, some value of x1 and x2 might have come closer to the final solution. And then you are exploiting that particular solution. That is known as the exploitation. Okay. I think it is clear.
Yes, sir,
Yes,
very
please.
much clear. Thanks for your time, sir. Thank you.
Okay. Now this, in most of the times in heuristic optimization techniques, we try to follow the behavior of a particular animal or a particular bird. Right. You might have seen in a pond. Okay. Suppose generally what happens, the ducks are moving in different direction, but after that they move in a particular line. Why they move in a particular line? Because unlike we humans, the birds and animals, they are not selfish. That's why most of these heuristic optimization techniques, they follow the behavior of ants and animals. They don't follow the behavior of human beings. Because among human beings, you would have exploration, but you won't have exploitation. Why you won't have exploitation? Because a particular human being, if he or she has written closer to the treasure, that information won't be shared with other solutions or with other humans. That's why most of the time, not most of the time, so most of the heuristic optimization techniques, they try to mimic the behavior of the plants, sorry, not the plants, the birds and the animals. There also, see, everywhere, what is the aim? You have to reach the destination. Okay. So here also, what is your destination? You are minimizing the function. You started with random value of x1 and x2. Now, what is your destination? Your destination is you change x1 and x2. And when you will say that you have reached the destination, when you have reached the final value of f, which is the least value of f, when you are minimizing error, or that value of f where the efficiency is maximized. Okay. And I think now is, if you have any question specifically related to your field, or if you have found some difficulty in terms of applying optimization to what you call this problem, then you can discuss it here. What I will right now do, I'm not discussing about the techniques. Maybe we can have another session where you can discuss the techniques. Now here, let us try to look at this problem. This is a research problem that we have solved. Now you have the system, you have the controller, you have a simple PI controller. Okay. Now what was your aim? Your aim was to solve these 4 nonlinear equations. Now what was given to you in the problem? I'm not going into core control system here. 2 unknowns are there, KP and KI. You have to find out, and where these KP and KI are there. Yeah, I think it is better to look at these 4 equations, which are highly nonlinear, which are highly complex. Okay, right. And here, just a minute. Yeah. The 2 unknowns are KP, which is here, and KC, which is here. KP and KC are the 2 unknowns. All the other variables, omega, Z, all of them are known. Right. Now your job is to find out the value of KP and KC. I am taking here 4 equations. You might think that 2 unknowns are there, so we might have to go for only 2 equations. But when there is a complexity, where there is a time varying nature, even to find out 2 unknowns, you have to need more number of equations. Now look at these 4 equations. From where these 4 equations have come, that's a different thing. But let us now look at as a pure mathematical problem, not as a control problem. 4 equations are there, 2 unknowns are there, all the other parameters are known. How will you find out these 2 parameters, KP and KI? Had it been some alpha x1 plus alpha 1 x1 plus beta 1 x2, alpha 1 2 x1 plus beta 1 2 x2 is equal to C1 and C2. Suppose we have to find x1 and x2 and all the other variables are known. You could have easily taken the inverse of that matrix and solved there. But here the problem is it is a highly nonlinear and complex problem. So here optimization can be used. How optimization can be used? Let us start with some random value of KP and KC. Okay, that random value of KP and KC, I put it on the left hand side and I calculate what is that I have on the right hand side. That random value of KP and KC I put on the right hand side of this equation. I find out what is that I have on the right hand side. Okay, I do it for all the 4 problems. I find out the left hand side and the right hand side. Now all the parameters are known because KP and KC also I have taken some random value. Now suppose none of the equations, the left hand side becomes equal to the right hand side. It means what? The value of KP and KC that we have taken is not correct. Okay. So in this case, what is your f of x? Or what is the function that you are trying to minimize? You are trying to minimize the difference in between the left hand side and the right hand side of all these 4 equations. And what is x? Your x is KP and KC. So in this problem, what you have to do, you start with some random value of KP and KC, and then you go on updating the value of KP and KC such that you arrive at a point where for all the 4 equations, the left hand side becomes equal to the right hand side. Once that happens, in that case, what you would have said or what you would have claimed that I have determined a value of KP and KC for which all the 4 equations are satisfied. Okay, right. So most of the times when you are designing a controller, like here for this particular problem, we have designed a controller so that a particular gain margin and phase margin is obtained. So how you have written these equations? these equations you have written it from the knowledge that you have regarding the control system. And once you have written the equation, then you forget about control system. It is a pure mathematical problem. Okay. Now, if you give these 4 equations to the mathematician and tell him, get me the value of Kp and Kc for which all these 4 equations are valid, that person may not have any knowledge about control system, but that person will provide you the solution. Okay. But if your equations are incorrect, he will provide you the actual solution, but that with that solution, you may not attain your objective of the desired gain and phase margin. Desired gain and phase margin, I basically mean the specifications of the control. Okay. So formulating the equations, from the equations which governs the system dynamics, use those equations to arrive at the objective function, then apply the proper optimization technique, then only whatever the solution that you will get will be proper. Otherwise, if you make any mistake, either in terms of framing the equations or framing the objective function or applying the optimization technique, you will not arrive at a proper solution. Okay, this holds for every application optimization in any branch of engineering. Try to appreciate this point. After you have obtained f of x, your knowledge regarding the system does not matter. The image processing problem, the signal processing problem, the power system problem, the control system problem, all of them are now looking to be similar. Once you have arrived at f of x, you only have to minimize it. Okay. Now here the question of optimization starts, or that heuristic optimization starts. But before that, to frame of f of x properly, you need to have proper knowledge regarding the system on which you are working. Until and unless you don't have proper knowledge regarding the system that you have working, you won't be able to write the equations properly and you won't be able to frame the function properly. Okay. So I'm not a very big researcher, but I have been using optimization for the last 20 years. Mind it, what I would be telling most of the students is that don't just apply optimization for the sake of applying, only thinking that since you have applied a new technique, your paper will get published. That might have happened 5 or 10 years ago. Now, getting a paper published in a good journal, it is a very, the benchmark is day by day increasing. Okay. I am acting as a reviewer for some journals. When I in a month or so, I used to get 1 or 2 papers from a particular journal. Now, that has gone up to 10 or 20. There has been increasing at least 5 to 10 times the number of papers that a particular journal is receiving. Many a times it is rejected at the test stage. So to avoid that, don't apply optimization just for the sake of optimization. First, you have thorough knowledge regarding the system, and then convince yourself, frame the objective function properly, and after that, of course, you can apply the most latest of heuristic optimization techniques. Okay.
Sir?
Yes, please.
What is the difference between the heuristic and the meta-heuristic techniques? Both are same.
There is not much of a meta-heuristic. Basically, you can think of it that the number of meta generally actually refers to more. So, okay, so when you have the number of parameters which are becoming more, then you go for this. See, basic, then you call it meta-heuristic. Heuristic, basically, the dictionary meaning is that we don't, go by a particular approach. And when you talk of optimization, when we don't go by a particular approach, it basically means that no hardcore mathematics is involved. Okay. So that is heuristic. And when you have the number of parameters to be quite high, that we generally call it to be meta-heuristic. The number of parameters in the sense, the number of parameters in the sense that the number of that x1, x2, x3, okay, like that. Suppose you are having a PID controller design problem where the number of unknown parameters are 3k, pki, kd. But if you are going for a state feedback problem, where if it is a 10th order problem, then the number of controller Turing parameters will be at least 10. Okay, so that becomes meta-heuristic.
Okay. Any other questions?
So differential evolution is applied under which scenario, sir? Differential.
You have asked a very good question. If you see, let us start from genetic algorithm, particle sum optimization, and differential evolution. Differential evolution, I also have experienced it that its convergence is faster as compared to genetic algorithm and particle sum optimization. You can say that it is one of the most fastest, and I won't say fastest because see, no statement can be given with regard to heuristic optimization. Every day, some new technique is coming. But it is very simple to implement in the sense that the number of tuning parameters in that problem is quite less.
Yes.
J algorithm is even more simpler to implement. It is almost parameterless. Okay.
Okay.
And differential evolution, the number of parameters are less. And in Java optimization, you don't have any parameter as such. Okay. So if you have the number of tuning parameters, just as you have tuning parameters for a controller design, you have tuning parameters for heuristic techniques also. So differential evolution has less number of tuning parameters, which you have to select on hit and trial basis, and the convergence is faster as compared at least to GA and PSO. This is what I have observed. But again, which technique is best? No proper guidelines can be given. It depends on the problem that you are solving. Okay. And it depends on the objective function that you are trying to minimize. So I cannot say that differential evolution is always the best. Artificial P colony is always the best. J algorithm is always the best. And one more thing that I have said you previously, if you solve your problem by any one of these techniques, more or less in 90% of the cases, you'll be coming down to a similar solution, whether you use GA, DA, not GA, but PSO, DE and all that. Okay. Now, suppose you are getting an improvement of 1% by using a particular technique. Is that enough to get your paper accepted? That is a very big question. Most of the times it is no. Okay. So again, I am saying that we are coming down to the same conclusion. Application is not important. Whether that application is adding a value to your domain, that is more important. Okay.
Yes, sir. Thank you, sir.
Any other questions? Any queries?
Morning, sir. My name is K. Manohar. For calculating best velocity, what is the approach we have to follow, sir?
I didn't get the question. You are saying that calculating the best velocity. You're talking of PSO specifically?
Yes, sir. I have compared with the PSO and the random search. As I said, with any of the optimization methods, we'll get almost similar results. So in this
are you getting or not? Now, first of all, tell me, you got almost similar result with any two technique?
Yes,
PSO and
random search.
Yeah. A random search. Now, let me answer your question.
In this case, yes. In this case, what is the method? What is the approach that we have to follow? Yes, sir. Yes.
Okay.
Same
I
question.
think I am not. Yeah. So your question was with regard to PSO. Now, yeah. First of all, you tell me if you run your algorithm for 5 times, for all those 5 cases, same algorithm, same problem.
No.
You run it 5 times. All the 5 times you got the same answer or you got different answers. First, you tell me that.
In random search, we got different answers, sir, and different values.
And in PSO?
PSO also, PSO not
You got
same, we got in more number of iterations. More number of iterations.
But
finally, all with a small error we got. So,
you're saying that smaller deviation, no? But they are not exactly same.
Not exactly same.
Okay. Now, but how will you ensure that which among the 5 is best? That whichever gave you minimum. But are you sure that if you run it for another 5, you won't get a better solution? You're not sure, no? Whatever the minor variation that you are getting, you are not sure. You ran it for 5, you got the best. For another 5 times if you run, there is a possibility that you may get an even better solution. However small, minor it might be. Yes or no? More?
Yes, sir.
Okay.
Yes, sir.
Now, this is again a problem with heuristic optimization. Now, what your question is that if I get your question properly, how you can ensure that in one go, I will get the best solution?
Is it?
In one go, we don't get, but we'll try to see with respect to other parameters.
Yeah, that is the catch here. Here in particle sum optimization, see, I have talked of parameters W, C1 and C2. These are the tuning parameters of the particle sum optimization. Generally, what we do, we take some random value of W, C1 and C2. Right?
Yes.
And in the books also, somewhere they have written that the value of C1, C2 and W should be this much. In some of the papers, they write it. But the problem is, there is no universal formula to get the value of W, C1, C2 in the best manner. So for my objective function, the value of W, C1, C2 might be something else, the best value. And for your problem, the value of W, C1, C2 must be something else. So what you have to do, and there is a problem, it is purely on hit and trial. You have to change the value of W, C1, C2 in such a manner so that at one point of time you get a W, C1, C2, that is the tuning parameters for which the results are best. Okay, but again you have to do it on a hit and trial basis and there is no generalized formula to get it. So that is why we call it as heuristic optimization. There is large amount of stochasticity and randomness that is involved here. So always keep in mind that whenever you are using heuristic optimization technique, if you are getting a solution, that may not be the best solution, that you cannot claim it that is the best solution. For that, you have to run the algorithm infinite number of times, which is practically not possible. But yeah, what you can always claim is that that particular solution is is somewhere close to the optimal solution, very close. Maybe 1 into 10 to the power of minus 5 or 1 into 10 to the power of minus 6. Okay. And regarding your velocity, I can tell you, nobody can claim that this is the best velocity that I have obtained. This is the best convergence that I have obtained. That can only be done by running the algorithm, running the program infinite number of times. So what we can do, you can run it large number of times, and within that, whatever the best that you have obtained, that you can claim it as the optimal solution. Yeah, is it clear, I suppose?
Yes, sir, exactly. Thank you, sir.